You know, every single time you refresh a web page or you book a flight or stream your favorite show, you're tapping into this huge, invisible world of systems. So today, we're going to pull back the curtain on the incredible architecture that really powers our digital lives. Everything from the internet's traffic cops to the impossible choices that engineers have to make every single day.
Wow, we have all been there. You know the feeling. Tickets for that one concert you have to see go on sale. You're on the site right at 10 a.m. sharp. You click buy, and boom, the whole thing crashes. You're just staring at an error message, totally frustrated. And you're thinking, why can't these giant websites just handle the traffic? It seems so simple, but what's really going on behind that error screen?
Well, when you boil it all down, the problem really is that simple. Just imagine a single doorway with 1,000 people trying to rush through it all at the same time. It's chaos, right? That's exactly what's happening to the website server. Every click, every refresh, that's a person trying to get through the door. And when there are just too many, the whole system just grinds to a halt. So, how do you solve a digital traffic jam like that? Well, you don't just build a bigger doorway. No, you add a bunch more doorways, and then you hire a traffic cop to direct everyone efficiently. And this is where our first big idea comes into play. It's called load balancing. A load balancer is, well, it's pretty much exactly what it sounds like. It's a piece of hardware or software that sits right out in front of a whole group of servers. So as all those requests for concert tickets come flooding in, the load balancer is the one that catches them and then smartly hands them out across the entire team of servers. It makes sure no single server gets totally buried, and that keeps the website online and running smoothly for you.
So how does this traffic cop decide where to send each request? Well, the simplest method is something called round robin. It is incredibly straightforward. The first request, that one goes to server A. The very next one, server B. The one after that, server C. And then it just loops right back to the beginning and starts over. It's simple, it's predictable, and honestly, it works great when all your servers are pretty much identical.
But wait a minute. What if some requests are way harder than others? You know, one request is simple, the next one is super complex. Round robin doesn't really account for that. So a smarter approach is the least connections method. With this one, before sending a new request, the load balancer takes a quick peek and asks, okay, which server is the least busy right now? It finds the one with the fewest active connections and sends the new work there. It's a much more dynamic way to balance the actual workload in real time.
Okay, so load balancers are awesome. We get it. But what happens on a day like Black Friday when the traffic is so insane that even with perfect load balancing, all of the servers are completely swamped? Well, then you have to form a line. And that brings us to the fascinating science of waiting.
Believe it or not, there's a whole mathematical field dedicated to the study of waiting in lines. It's called queuing theory. It allows businesses to analyze every single part of a queue, from how fast people show up to how long it takes to help them, all to make really smart decisions. It is the entire reason that virtual waiting rooms exist when you're trying to buy those concert tickets.
And what's wild here is that this very modern problem of digital queues actually has roots that go back over 100 years. It all kicked off in 1909 with a Danish engineer named Agner Erlang. He was studying the telephone exchanges in Copenhagen, trying to figure out how many operators they needed. And his work laid the foundation for this entire field, which decades later became absolutely crucial for building the ARPANET, the network that eventually became our internet.
Here's the core idea in action. Queuing theory is basically the science that tells a supermarket manager when it's time to open another checkout lane. By modeling how customers are flowing in, they can predict how long the lines are about to get, and then add just enough cashiers to keep things moving without having people just standing around. It's the exact same math that applies to web servers. Now, the most fundamental model for all of this is something called the M/M/1 queue. I know, that notation looks super intimidating, but don't worry, it's just a shorthand. The 1 just means there's a single server, one cashier. The first M means that people arrive randomly, and the second M means the time it takes to help them is also random. It's the basic building block for understanding how these unpredictable queues actually behave. This quote from William Gibson, it just perfectly captures where we're going next. See, these load balancers and these queues, they aren't just isolated tools. They are pieces of a much, much larger puzzle. The future of the web is built by spreading all these pieces out across the entire globe, creating one massive, powerful system. But like the quote says, distributing that power evenly, well, that's the real challenge. So let's zoom out. All these individual pieces we've been talking about, the servers, the load balancers, the queues,
They're all part of a bigger structure, and that structure is called a distributed system.
So, what is a distributed system? Well, think of it like a huge team of independent computers that all work so closely together that to you, the user, it just looks like one single coherent, super powerful machine. Google's search engine, Netflix's streaming platform, your online bank, these are all gigantic distributed systems, coordinating thousands of computers behind the scenes to give you a totally seamless experience.
Now, here's the thing. Building these systems is unbelievably complex, and it forces the engineers who build them to make a fundamental and, yeah, sometimes an impossible choice. Because you just can't have everything. There is always a trade-off. This trade-off is actually formalized in something called the CAP theorem. The easiest way to think about it is as the great pick two of computer science. It basically says that any distributed system can only guarantee 2 out of 3 essential properties at the same time. You simply cannot have all 3. It's impossible. So what are the 3 guarantees you have to choose from? First, there's consistency. That means everyone sees the same, most up-to-date data, always. Second is availability. That means the system always responds to your request, no matter what. And third is partition tolerance. That means the system keeps on working even if parts of it can't talk to each other over the network. The CAP theorem says you have to pick 2 and sacrifice 1. A bank, for instance, will always choose consistency. They would much rather their ATM go offline than have it show you the wrong balance.
And that brings us right back to you. The next time you're using an app and it feels a little slow, but you notice the information, the data is perfectly correct and up to date, you can ask yourself, which 2 sides of that triangle do you think the engineers chose? They likely picked consistency and partition tolerance and sacrificed some of that immediate speed or availability. It's a completely invisible choice, but it's being made for you every single second you're online.